So how would we go about finding the escape velocity for a problem in electrostatics? So if we say we're starting with a source charge, positive, that's locked in position, and its attraction on a negative charge, which is a distance of r apart. And to work on this, we need to start with the conservation of energy. Energy total will equal the kinetic plus the potential. And for this situation, that would mean that 1/2 mv squared, the initial squared of this particle over here. And this would be the component in the direction of r. So if there was a velocity out this way, of course, we would take this component to work on this. So now that we've done that, the potential, like we say, is plus Ke, or 1/4 pi epsilon naught, whatever you want to do, Ke times Q1, Q2, and we'll just say this is Q1, this is Q2, over R. And this would be initial as well, based on what we're going to find what this velocity needs to be in order for the negative particle to escape the positive to the charged particle's attraction. So we can use the condition that this particle would need to reach r equals infinity with a velocity that is either 0 or greater than 0, which would mean that it successfully escaped the attraction of this positively charged particle. So because of that, at r equals infinity, the kinetic component must be greater than or equal to 0. And now we can work on another piece of this equation. So when k must be greater than or equal to 0, we want to see what the minimum velocity would be. So we'll just set the kinetic component to 0, and then plus, and then this at r equals infinity would be just 0 as well. And we'll work on the charges in a second, but total energy of the system would be equal to 0 when this particle has a velocity that will escape the system. So now we can set 1/2 mv squared, or v initial squared, what we would need to find for our escape velocity, equal to Ke Q1 Q2 over R. And this is interesting because we do care about the signs of the charges. Of course, Q1 and Q2 are going to be of opposite sign, which means that you can set these equal and not have to care about this negative, because this wouldn't work with our square root, and we know the signs are going to be opposite, so there's going to be a negative floating around, and it'll cancel that. So now we have 1/2 mv squared equals Ke Q1 Q2 over R. Given that the charges are of opposite sign, we can solve for V escape. So 2 Ke Q1 Q2 over MR group. And of course, the M would be the mass of the negatively charged particle, because the mass of this positively charged particle has no effect. Of course, the gravitational attraction will be magnitude 40 times less than the magnitude of the electrostatic attraction. So that leaves us with the escape velocity equation for an electrostatics problem.